The purpose of this video is to learn how to name carboxylic acids using the IUPAC International Union of Pure and Applied Chemistry nomenclature system. So let's get started on how we would go about naming molecules that have a carboxylic acid functional group. I've put the rules here for naming these molecules using IUPAC nomenclature. The first rule is going to be to find the longest carbon chain that includes the COOH group, that is the carboxylic acid functional group, that is the carbonyl group that's directly bonded to the OH group. That carbon is going to form the foundation of your longest carbon chain. When you're looking for your longest carbon chain, you will look specifically for that carbon atom, and from there, once you have found that carbon atom will always be carbon number 1 of the chain, and then you will number onward from there to find the rest of the carbon atoms of the longest carbon chain here in entry number 2 of our lineup for determining the nomenclature. The reason why the carboxylic acid group is always at position number 1 of the chain, and we find the longest carbon chain relative to that, is because we have a hierarchy for determining what the parent name is. The hierarchy for determining the parent name I've put here for reference. In the hierarchy, carboxylic acids are absolutely at the top of the hierarchy. So even if you have a molecule that has an aldehyde group, a ketone group, an alcohol group, an amine, or all of these anywhere in the molecule, the carboxylic acid is still going to take priority in deciding what the parent name is of the molecule and how to number the longest carbon chain. So in this hierarchy, if something is listed higher in the hierarchy, that means that is going to drive what the longest carbon chain is and what the parent name of the molecule is. So for example, if you had a molecule that had a ketone group and an alcohol group, the molecule would take the parent name of the ketone with an O-N-E suffix, and the numbering of the molecule would be determined relative to the ketone group, and then the alcohol would be referred to as a hydroxy branch. In the case of carboxylic acids, since if there's a carboxylic acid present, that's going to dictate the parent name, we need to talk about what that parent name would be. The parent name of a carboxylic acid is going to follow the template alkanoic acid, where we would just take the name of the corresponding alkane carbon number, such as methane, ethane, propane, etc., and replace the E of the alkane name with oic acid. So for example, methanoic acid, ethanoic acid, propanoic acid, and so on and so forth. So that's going to be our parent name. Carbon number 1, going to be the carbonyl carbon of the carboxylic acid group. We number from there, finding the longest carbon chain, and then we go in and name and number all the branches as prefixes in the name, much like we have done with the other nomenclature we've worked with so far. So let's go ahead and do an example of how we would go about taking care of this. So in our example, I'm going to draw out the structure of a representative carboxylic acid as a line angle formula here. And we're going to use this as our example problem to illustrate how we would go about taking care of this. All right, so in this molecule, you will notice that I do have some chiral centers. That is, carbons that have 4 different groups bonded to it. Those chiral centers we would find in the structure here and here, but we don't have wedges and dashes shown at those, and therefore we will not be determining whether those are R or S. You can only determine R or S in line angle formulas if there are wedges and dashes. Otherwise, we can recognize that yes, these are chiral centers because chiral centers are just carbons that have 4 different groups bonded to them, but we can't say whether this is R or S. It's just undefined, and so we won't include that information in the name for the molecule that we're working with here. All right, so finding the longest carbon chain, we begin here 1, 2, 3, 4, and 5. And now we're going to number the branches coming off of that 5 carbon chain, where the 5 carbon chain would be referred to by the parent name pentanoic acid. So I'm filling in the name pentanoic acid. And then I'll plug in my branch names here. I'm going to go ahead and highlight my branches. So my branches are the bromine branch, my methyl branch here, and then don't forget the alcohol branch down at this end. And we already incorporated the carboxylic acid group into the parent name, so that's taken care of. We don't need to worry about that. So at position number 3 of the chain, we have a bromine or bromo branch. At position number 4, we have a methyl branch, and at position number 5, a hydroxy branch. So plugging those in as names here in alphabetical order, as we always do. Name and number all branches in alphabetical order. Number 3, bromine, is going to come first in the alphabet, so I'm going to call this 3-bromo. And then hydroxy comes second in the alphabet, so I'll call this 5-hydroxy. And then methyl comes last in the alphabet, so then we go 4-methyl. And the word methyl runs directly into the word pentanoic acid. No space needed in between because we have no numbers there, and we use dashes to separate numbers and letters. But if it's just letters, we run them right together. We do put a space between pentanoic and acid per the IUPAC rule, so it's no coincidence that I have a little gap there. Let's go ahead and name one more molecule as we wrap up here. Now for this molecule, we have an aromatic ring that has a carboxylic acid group bonded to it and an amine group. This problem is going to require that we remember the rules that we learned for naming molecules that have an aromatic ring bonded to a carboxylic acid group. And back in a previous chapter, what we learned when talking about this was we learned that the parent name for an aromatic ring with a carboxylic acid group bonded to it is referred to as benzoic acid. So I'm going to go ahead and put the name benzoic acid in there this time as the parent name, because when we're naming molecules that have aromatic rings that have a carboxylic acid group on it, the parent name becomes benzoic acid. And then from there, the numbering system is that we number starting at the carbon out of the ring that has the carboxylic acid group on it, the group that gives the parent name. Take the shortest route around, so we're going to go around the molecule this way because it's a shorter path to the amine branch than going the other way. And then at position number 3, we have our amine group, and an amine branch is referred to as an amino group. So an amine branch is always referred to as an amino group. Much like what we called a hydroxy group was an alcohol that is a branch, an amine branch is an amino group. So at position number 3, we have our NH2 group, so I'd call this 3-amino benzoic acid. And a synonym for that would be, we could also refer to this as meta-amino, because if we have 2 branches on an aromatic ring and they are positioned like so, where we have branch, nothing, and then a branch, we refer to that orientation of groups as being meta. What if we had a molecule which had no aromatic ring? How would we go about doing that? What if instead we had a non-aromatic ring? So here we have a molecule that has a 6-member ring, but notice it's not an aromatic ring. And so therefore the parent name is not going to be benzoic acid like it was in the previous example. Instead, it's just going to be cyclo, referring to the fact that the atoms are in the ring, hexanoic acid. So we have our cyclohexanoic acid, and that name that we have incorporated will encompass the 6 atoms of the ring and the hexanoic acid. It's implied that the carboxylic acid group has to be at carbon number 1, because that's what's forming the foundation of the parent name for this molecule, and the carboxylic acid group will always be at position 1 of the ring. So we go position 1, 2, 3, taking the shortest distance around to the branch. And remember that an aldehyde or ketone branch, like we have here, this is a ketone branch, is referred to as an oxo group. So therefore, we would call this a 3-oxo group. It is not appropriate in this case to call this a meta group. We could not call this meta-oxocyclohexanoic acid because the term meta only applies to aromatic rings, and we don't have an aromatic ring here. So instead, we cannot use the meta designation to indicate the location here. Instead, we have to use the number 3 to refer to as 3-oxohexanoic acid. So as a review, when we're looking at groups that are coming off the ring or coming off a chain as branches rather than as the parent name, aldehydes or ketones are both referred to as oxo branches, alcohols as hydroxy branches, amines are referred to as amino branches, Alkenes and alkynes are going to be incorporated into the parent name. You would have a parent name that had both the alkene group incorporated or the alkyne and whatever else was there. So it would be hexene oic acid, for example, with a number designating where the alkene group was. And then alkyl and halogen branches, alkyl groups are referred to just as methyl, ethyl, etc. Halogens are referred to as halo branches with the specific halogen represented, such as fluoro, chloro, bromo, iodo. And that will take care of our hierarchy. So with this information, you should now be comfortable with going about determining the IUPAC names of carboxylic acids that have at least one other functional group present within the chain or around the ring of a di-substituted ring, such as what we have here. We have two branches coming off of the ring.